In a recent YouTube video, Fran Blanche on her eponymous channel posted a video entitled Resurrecting a Vintage Numitron Board. She had come into possession of a 7-digit Numitron display board with some driver logic, some transistors and so forth, obviously vintage. And she's talking about how to use it, how to drive it, and all of that is great. She then wondered what she's going to do with it, perhaps to display it better. And the first obvious idea that came to mind was, well, what about a clock? And she rejected that because she felt that leaving Numitrons running all the time would shorten their life. Because after all, they are incandescent bulbs, incandescent displays, and presumably they have a limited lifetime. She suggested perhaps a calculator would be a better application to show them off, because obviously a calculator isn't left on all the time. So this caused me to break out my my clock made out of what else? Numitrons, because I want to talk to you about how long this thing's been running and how I keep the Numitrons running basically indefinitely. So here it is. These are IV9 Numitron tubes, courtesy of somewhere in Ukraine, many years ago, by the way. It was a prototype of a Numitron clock, and I decided to leave it as such and mount it in a display case. So let's power it back on. And it comes to life, and it sets itself because it gets its time from a DS3231 module. And so here it is, and this clock has been running continuously for something on the order of 7-8 years. I forget exactly when I put it together, but I haven't changed anything on it. It just runs, and it never gets switched off. And so, originally I thought, well, aren't I going to design at least a PC board to properly mount all this stuff? And yeah, I was going to, but then I decided this thing looks so ridiculously janky that I thought I'd leave it in its state, put a display case around it to protect it, and it's been doing just fine. It's so much of a prototype that there's not even a way to set the time in this clock. The way I do it, if I ever have to, which I don't because the DS3231 is just such a great chip, is that I pull the module out of its little tiny breadboard, and I plug it into a fixture that I created, which automatically sets it to the correct date and time from an NTP server. And then I plug it back into this clock, and it all works perfectly. So I didn't even bother putting in time setting switches and logic here because it really isn't necessary. I wanted to talk a little bit about the architecture of this particular Numitron clock that I built, in case you find it of interest. The best way I found to do this is to lay out all the components of the clock, -1, which you'll see in flat here, without all the wiring clutter of the clock, which you saw elsewhere, and which actually makes it look like it's so janky. So here is basically every component except the integrated circuits. Starting on the left here, we have, of course, the DC barrel power entry. Whatever DC you feed here gets stepped down and regulated by 2 of these DC to DC buck modules, one of which I have set to output 5 volts, and that runs the logic, the processor, and the DS3231 clock module. The other one here, I usually set to around 4 volts, but could set up to 5 volts, and that strictly runs and supplies filament voltage to the Numitrons. And that way the Numitrons can have their filaments can have a separate supply voltage from the logic, and this helps if I want to dial down the voltage on the Numitrons in order to prolong their filament's life. On top here, on the right, we have an Arduino Pro Mini. This is kind of my little go-to processor, an ATmega 328, an Arduino chip. Nothing fancy, but it gets the job done very easily. Next to it is a DS3231 real-time clock module. You see these all everywhere. They are, of course, battery backed, and I can't say enough good things about the DS3231 chip from Analog Devices. It is wonderful, and its successors. And I have videos on it elsewhere on the channel. There's a 10K pot here, which I use to create an analog input for the processor, and it reads this, and then based on that, it outputs a PWM pulse trained, a varying pulse width in order to modulate the output enable of the TPIC 6A595 chips, which are not shown here, and that I do to modulate the intensity again of the Numitrons in order to prolong their life. On the larger breadboard, I have mounted, sticking up, and just plugged into the breadboard by its leads, 6 IV9 Numitrons, courtesy of Ukraine. These are relatively small Numitrons, but they look pretty nice. There's 6 of them. What isn't shown here are the chips, the shift register chips I use. So this clock does not multiplex the displays. Each display is driven separately by its own shift register, 8-bit shift register, and for that I use the TPIC 6A595, which is not shown here because I didn't have any spares, strangely enough. They're all in the clock right now. But basically it works pretty much like a 74595 8-bit serial shift register in, and each output of the shift register drives one of the segments of the Numitron, one of the 7 segments, including the decimal points. Since serendipitously, a 7-segment display with its decimal point has 8 inputs, and this shift register had 8 outputs, so that works very well. I'll go over the TPIC 6A595 shift register elsewhere in the video. Plus a scattering of decoupling caps for the logic 5-volt rail. And that's basically the clock. Let's take a quick look at the TPIC 6A595's datasheet. It operates basically like a classic 595, except of course the pinout's different because you'll notice it's a 20-pin dip, and that's because they had to accommodate a lot of extra ground pins here to handle the sync current that this thing's capable of switching. Apart from that, you'll notice it's rated to 350 milliamps per output, and up to 50 volts, so that's quite significant. Again, I don't need this kind of power capability. I just happen to have these. I just happen to have 6 of these, so I use them. And here's the block diagram of the TPIC 6A595. Basically, the left-hand side of this looks pretty much like a stock 595. Where the chip significantly differs, of course, is on the right-hand side, the output side, if you will, or input, depending on how you look at it. So basically, this can drain any kind of positive voltage up to 50 volts that you apply to the drain lines here, and it switches them to ground individually. So in the displays, I simply, the common of all the displays goes to plus voltage, and then each individual segment comes into one of these, and then it gets switched to ground to turn it on. The other thing on the left here, the input here called NUT G, which is output enable on a 595. This simply turns all the gates on and off, and I use this to with the PWM output on the Arduino simply to modulate the brightness of the displays to set, and that's how I set the brightness. Of course, I also set it using a separate supply voltage to the to all the filaments. So because each segment is connected to 1-bit output of each shift register, I have total control over lighting up any segment on any display. Obviously, for this clock, I want to light up digits, so I have to create my own table. And so here the segment table for all the digits between 0 and F. Of course, I don't use A, B, C, D, E, or F in the clock, but they're there anyway because This was only a prototype, and I was going to use the displays for other stuff as well. Nice things about the Arduino libraries is it makes working with shift registers absolutely ridiculously easy. Here's the entire routine, which displays the current hour, minute, and second, which it gets as 3 bytes. We separate out those into 6 individual digits. We set the latch, turn the latch so that we can we shift out using the data in the clock pins of the 595 shift registers, and an entry in the lookup table you just saw to send the right byte for the right digits with the right segments in the right place, and then we latch that in and we lather, rinse, repeat. Again, really, really simple stuff. So each display's common is being fed plus 4 volts, and then the 595s are draining the individual segments current to turn them on or not. In addition to varying the input voltage to the displays, I also have a little potentiometer, the little blue thing there, and I programmed the Arduino so that by adjusting this, I can adjust the duty cycle on the not G input of the 595, which is basically the output enable. So by sending a different with pulse train, and in Arduino this is ridiculously simple to do, of course, you notice I can adjust the brightness, and then for the net current that each display is going to be passing. So by adjusting this and the input voltage, I can basically set it to anything I want. And by running it fairly dim and at fairly low duty cycle, I expect these Numitron segments to last basically indefinitely. So that's a tour of my Janky Numitron clock.